Okay, so this is Mrs. Gorley. This is the BC Calculus lesson 4.4, which is on finding increasing and decreasing intervals of a function. So in 4.3, we found absolute extrema on a closed interval, where you found the very highest and the very lowest y value there. Now we want to find the relative extrema for an entire function. So now we're not going to have a closed interval, it's just going to be the whole thing. So how do you think this is going to be the same, and how is it going to be different? What do you think? How would it be the same as finding absolute maximum on a closed interval or minimum? Yeah, you're not going to have just end points. It's going to go on forever. So does it go forever up? Does it go forever down? Does it go to a horizontal asymptote? Those kind of things. So there's one thing, is you don't have ends anymore. But how did we find the maxes and mins on the closed interval? What was our process?
Find the derivative and then put it in and all your endpoints into it.
Right. So we found the derivative, right? So we're going to have to do that again. What did you do with the derivative once you found it?
Set it equal to 0.
Right, we set it equals 0, or where it does not exist, where the original function existed but the derivative doesn't. So that process is going to be the same. We're still going to find the derivative. We're still going to set it equals 0. But now, instead of just a closed interval, we want every place that it equals 0. So we're not just looking at this little area anymore. Okay, so let's go to this. And I want you guys actually in class here, we're going to do this up at the boards. So I'll just freeze it here. Okay, and for those of you watching this video at home, I want you to try to see if you can figure out just intuitively, how would you find where this increasing is going up and going down, or where it's like constant, staying the same y value. All right, so we just did these on the board in class, and what we found was that we actually have, the graph looks something like this over here on the right, this picture that we have. So it goes up, then down, then up. And we found our critical numbers by doing the derivative and setting it equal to 0. We're at 0 and 2. So that means this value here, where you have 0 slopes, this was when x equals 0, and this one here was when x equals 2. So there was lots of different ways that we did this in class, but basically what we're going to do each time is do a number line. The number line, I think, is one of the easiest ways to organize your information here. However, you have to realize that a number line is never considered work on a calculus test. It's just a little thing that you can do off to the side to help you organize your information. Now, I should say on the AP exam. On our tests, I want to see it on all of them, just because I feel like it's a good way to help you do these. But what you do is you just put your critical numbers on the number line, and then you test each section. So we do like f prime of something in this section over here. So anything less than 0, so just pick an easy number less than 0. If you plug in a -1 there into the derivative, you get a positive value. So therefore, everything from 0, or from to the left of 0, which on our graph is like this part, you can see that part is increasing as you go from left to right. And then you do the same thing on the other one. So we set up our f prime of something between 0 and 2, so like 1, and we get a negative. So therefore, it's going down between those, and then you pick something above 2, like maybe 3. Any number, it doesn't matter what you pick, any number above 2, when you plug it in that derivative, will give you a positive value. So I don't really care what the number is, I care if it's positive or negative. So you notice on here, I didn't write the number, I wrote positive or negative. That's what you're looking for. And then you can say, oh, okay, so it's positive. If the slope is positive, that means it's increasing from -infinity to 0, and then again from 2 to infinity, and it's decreasing from 0 to 2. Okay? All right, so let's go on to our next question then. So what if the graph is not continuous? How is that going to change things as far as increasing and decreasing goes? What do you think? For instance, think about what if a graph has a vertical asymptote in it? Is that going to change? Could that affect increasing and decreasing? Yeah, I mean, think about it. Just throwing one on here. If I put, say, a vertical asymptote right there and maybe a horizontal asymptote here, I mean, you've got the graph could be increasing there, and then at the vertical asymptote, it could change to decreasing there, right? Or it could still be increasing after that. It could be something like this, where it's increasing on both sides there, or instead of that, it could be increasing and then decreasing on the other side. You know, it's got lots of different things. So at any place where the function doesn't exist, it also can change increasing or decreasing at that point. Okay, it can change directions at that point. So basically now, one of the big things that we have different about finding increasing and decreasing intervals, not only do we have to find critical numbers, but we also have to make sure that the graph is continuous, and if it's not, we need to find where is it continuous. So just like last time we said we had to have, when we were doing absolute extrema, we said we had to have a continuous closed interval. This time we have to have continuous, and if it's not continuous, we have to find any place where the function does not exist. So basically you have to find the domain of the function first. So let's look at up here on the last one that we did, that first one, the domain of any polynomial is all real numbers, but this one is the domain all real numbers again. What do you think? What can't x equal? Right, x cannot equal -1. So you could think about this from the graph. You could say, well, okay, I know that this has an asymptote then at -1. Where else? Where's a horizontal asymptote on this one? At 0, yeah, because the power on the top is smaller than the bottom, so the horizontal asymptote is right at this axis here. And then you could just maybe plot a couple points on here. If you plug in, say, 0 for x, you get the 0.1, so the 0.01. So that means this part of the graph is stuck right in there. And do you remember about the multiplicity on asymptotes? Did we talk about that in this class? We did, didn't we? So if it's got an even multiplicity, because this occurs twice here, then what happens at this asymptote? Since the right side is going up, what's the left side have to do? Has to also go up. Yeah, remember when they're even multiplicity, they go the same direction. If it was odd multiplicity, the left side would be going down, but it's got to go the same direction up like that. So we can look at it without even doing any calculus on this, just by knowing some algebra, and we can say it's increasing from -infinity to -1, and then it's decreasing from -1 to infinity, right? Okay, but how would we do this using calculus? What would I do first? Find the derivative. So what's y prime here? Let's rewrite y. I mean, you can use the quotient rule if you want, or you can just rewrite this as x plus 1 to the -2. Is that okay? Anytime you have the numerator just has a number in it, then you don't have to use the quotient rule. You can bring the denominator up as the negative power. So do the power rule on this, and what do we get? Yeah, x minus 1, or x plus 1 to what power?
-3.
Right, -3? Yeah. So yep, subtract 1 from it. Lots of people want to put -1 on there because we're used to saying, you know, like that. And then multiply by the derivative of the inner function. Don't forget that. In this case, it's just 1. So really, we have -2 over x plus 1 cubed, right? But what's the domain of this derivative then?
Still doesn't equal -1.
Right, still doesn't equal -1, which was what our original one was. So even though this derivative doesn't exist at -1, that's not a critical number because it wasn't in the domain to start with, -1. So what you first do on these, the process on these, is you look at the domain, and on your number line, you're going to put anything on the place where it doesn't exist. So you might want to put what it is so that you remember. This wasn't a critical number, it's a vertical asymptote. Okay, and then we look at where does the derivative equal 0 or does not exist. Well, it doesn't exist at -1, but that was already the vertical asymptote, so we don't need it. Is there any place where this equals 0? No, the top is -2. That can never equal 0. So there's no critical numbers for this. And then you just do the same thing we did before. You plug in a number to the left of -1, like something over here, into the derivative, and we find out we get a positive number when we do that. Then we plug in a number to the right of -1 into the derivative again, and we find out we get a negative number, so therefore it's decreasing over there. Okay? So the point is, we didn't even really need to do this graph up here. We could have done just the calculus work that we did down below without ever graphing it and finding out where it's increasing and decreasing. All right, so let's do one where you've got both kind of things going on this one. So instead of graphing it, I mean, we could graph that. Where does it, what's the domain there? Right, x cannot equal 1/2, so that's where the vertical asymptote is, right? So if we put our number line, we can put 1/2 on there already, and we'll label it as a vertical asymptote. Okay. Now we need to find the critical numbers, though. So what do I do? Right, dy dx or y prime. Now, can I just pull the denominator up as a negative power this time? I mean, you could, but then it makes it actually worse to do that. So we're just going to use the quotient rule. So low d high minus high d low all over the square of what's below. And then we'll simplify that. What do we get? 4.
2x squared minus 2x over 2x plus 2x minus 1 squared.
Great. So because we end up with 4x squared here and then minus 2x squared and then minus 2x over this guy. Okay, so can we set this equal to 0? We already know it doesn't exist where x equals 1/2, right? But that was our domain, that was our vertical asymptote, so that's not a critical number. But if you set this equal to 0, how do you solve this part when you set that equal to 0 to find critical numbers?
X is 0, 0.
Yeah, x is 0. Is that the only place?
1.
When a fraction equals 0 like this, which part of the fraction equals 0?
The numerator.
The numerator. So basically we just have to think about the numerator equal to 0. Because basically think about that. If you multiply the denominator on both sides, you're just going to get this, what I've written right here. What if we factor out a 2x? Yeah, you get x equals 0, but what else do we get?
X equals 1.
Right, x equals 1. Those are our critical numbers. So then put those on the graph. So we have 0, and I'll label it as a critical number, and 1, and label it as a critical number again. Okay, so now that I have I have all my critical numbers, and I have all my domain issues on the number line, how do I check to see where this is increasing and decreasing?
Left and right of each one of those.
Exactly. Let's pick something to the left of 0 here. So just do f prime, or y prime, actually. We don't have f here. Y, we'll say dy dx, so different notation, evaluated where x is equal to, say, -1. So plug a -1 in here. And you don't even need to know what it is. Just is it positive or negative?
You only need to test 2 areas.
Why?
Because if you test between, or rather before 0, then you know what after 0 and between 1/2 is. Then if you test either before or after 1, then you know what the other one is.
You would think, and I'm so glad you brought that up, because it doesn't mean every critical number. Well, let me ask you this. Like last time when we talked, when we found a critical number, was it always a maximum or a minimum? No. So you do be careful, because that's very common where people want to just check one section and then they assume the others alternate, except for you said around the vertical asymptote. That we don't know, right? But around critical numbers, people want to assume that they alternate, but it's not always true. So you need to test every section. Now, if you're really good at graphs and you know, like I know what this graph looks like, then you can get away with some things. But you really should be testing all of them, especially because you want to show them that you know the process. And it's kind of lame, but sometimes if you are a higher thinker and you've actually, like, you've figured out some things like that from graphs and things like that, if you don't show it to them somehow, they're not going to give you full credit. So you're better off to just go back to that, okay, I'm just going to show them every section, okay? So if we plug in something to the left of 0, like -1, into our derivative here, what do we get? What do you get when you plug in -1 there? Is it a positive or a negative? It's a positive? Do you guys agree? What do you get? Yeah, 2 plus 2, so you get 4 over. Obviously, the bottom's always positive, right? Because you're going to square it. So that's a positive, so we know it's increasing there. And then between 0 and a half, let's do, let's plug in x equals, say, 1/4. Okay, what's that going to be then? 1/4. So I'll have 2 times 1/4 squared, which is 1/16, minus 2 times 1/4 over something positive. So we end up with 1/8 minus 1/2 over something positive. Well, what is that, positive or negative? It is negative, yeah. So it decreases there. And then you need to check something in between. Whoops, I should put there, this is decreasing. Then we need to check.
Since it's the vertical asymptote, and we know the multiplicity is not.
Very good. So this is one place where the multiplicity, yeah, you could save a step there, because you can say, because the multiplicity on this is 1, then you know that they go opposite directions, right? So if this side is going down, what's the other side have to be doing? Going up. So what does it mean the graph is doing there? Wait.
They're both decreasing.
Yeah, because you got to think about it. Like if you have this asymptote at 1/2, and this side is decreasing, so it's going down like that. The other side, since the multiplicity is 1, it's got to be like that. So it's still decreasing on that side. You might be better off if you don't get that with the multiplicity, because I could see people going, oh, it has an odd multiplicity, and then saying, oh, that means they're opposite, and then saying it's increasing there instead. So you might want to just plug in 1/4 into the derivative. And then, let's see, or not 1/4, 3/4 into the derivative there. We need something in that section. Okay, and then our last one, we need something to the right of, let's see, we'll plug in x equals, say, 2. If you plug in a 2 there, do you get a positive or negative? Yeah, you get a positive again. So we've got our increasing intervals are going from -infinity to 0, and then 1 to infinity. And then our decreasing intervals are going from 0 to 1/2. And could I just say 0 to 1? Right, because you can't include 1/2 because it's not in the domain. So you definitely have to put them as 2 separate intervals. 1/2 to 1. Okay, now my other question to you is, what about where they come together here? Like at 0 here, let me highlight this. At 0 and 1, all of these places there, where it changes from increasing to decreasing the critical numbers, should you put parentheses like I have it here, or should you put brackets? What do you think? It's kind of weird because the AP won't take off points whichever one you put. They'll give you either one, because there are some books, like the calculus book that I learned from, always put parentheses. But AP, they say it's more correct to put a bracket because the actual definition of increasing just means that as you move to the right, you're getting higher values. So they're saying, well, yeah, it's increasing all the way up to and including that endpoint there. So they include it, but then they include it in decreasing too. So the book that I had, they were like, well, you can't be increasing and decreasing at the same point. So they always put brackets on it. But AP says you're just talking about each section individually. So you should put, my book put parentheses on it. So AP says put brackets on it. But they realize that this is an issue, kind of a controversial issue, so they will give you either one, okay? They don't really care. So I always just put parentheses on everything, but they actually like brackets better. But that's the way I learned it, so I think I just kind of go back on that. All right, so let's go to your book. So you have this list of instructions, exactly what we just did on these first problems. We're going to find the domain first, and we list that, and then our critical numbers, where either the derivative equals 0 or is undefined. But remember, where it's undefined, it had to be, that can't already be where the function did not exist. And then we're going to make a number line, and we're going to put all of the domain restrictions and the critical numbers on the number line. Then we're going to test each section and find out are they positive or negative. And then we're going to state whether they're increasing or decreasing. Okay? And then from that increasing and decreasing, you can obviously then find the minimums and maximums. Wherever it changes from increasing to decreasing would be a max, and wherever it changes from decreasing to increasing would be a minimum, right? So those are our relative extrema. And if requested, then we give the y values or the points, but most of the time you're giving just the x values on these things, okay, unless they say otherwise. So this is that whole thing about AP that they really tell you that you should put brackets, but they aren't going to penalize you if you don't. All right, so let's go to example 1. Everybody ready? So find the intervals on which these functions are increasing and decreasing, and find all local extrema or relative extrema points. So when we're done, we got to have our answer as points this time, because they said write points. Okay, so what's our first step?
Find the derivative.
Yeah, we could do that. Does it matter which you do first? What's the other thing you have to do at the beginning? Domain, yeah. Does it matter if you do domain or derivative first? Makes no difference. Their list says to do domain first, but it doesn't matter. What is the domain, by the way, here?
All real numbers.
Why is it all reals?
Because there's no x's being divided or anything.
Yeah, there's nothing being divided, but what does that mean right there?
It's a cube root, not a square root.
Right, it's a cube root. And so if it's, remember the number on the bottom of the fraction up there and the power means the root. So as long as you have an odd root, you can take the odd root of anything. If it would have been to the 3/2 power, then we'd have an issue, because you can only take the square root of positive things, okay? But we don't. It's raised to the 2/3, so it's all real numbers. So you're looking for any place that makes the denominator equal 0 or any square roots that you can't put negatives in. All right, so we know our domain is all real numbers, and then what do we do next then? Katie, what did you say?
Take a derivative.
Right, derivative. So what rule are we using? Power rule, yep. Let's see. So is this right? Let's see. I see this all the time. Is that right, what I did? What did I do wrong? I thought I needed a chain rule here where I do the derivative of the inner function. I did it. Right. I didn't chain it on. I just stuck it inside there. Remember, you keep the inner function, subtract 1 from the power, and then what goes out here?
The 2x.
Right, that's where the 2x goes, the derivative of the inner function.
Does it matter where it's at since it's all multiplication anyway? Like, could I put it in front?
Yeah, you could put it in front if you want. In fact, I'm going to simplify this a little. So it'll make a 4x over 3, and I'm going to write it as cube root just so that because for me it's easier to visualize. If you want to leave it to the 1/3 power, that's fine. Okay, so now at this point, what do we do?
Find the domain again.
Okay, why do we need the domain again?
Because we need to know, like, if there's, like, holes or something.
Right.
The derivative.
Yeah, we need to know if there's holes in the derivative. Well, basically, this is that second part. Remember, we said critical numbers occur where the derivative equals 0 or does not exist. So that's the domain of this guy. So it doesn't exist where? How would we do this? Does not exist. How do we find that?
The denominator equal to 0.
Right. When does the denominator equal to 0? And I don't really need the 3, basically, right? Because I could just divide that off. I'm just looking at where is this part that has the variables in it equal to 0. Well, you can cube both sides there. So it's just saying where is this equal to 0? Where's that at? Yeah, positive and negative 3. Okay, if you add 9 and take the square root, don't forget plus or minus, or you could factor that x plus 3x minus 3. So those are critical numbers. Are they the only critical numbers? What do you think? What else do we have to do to find critical numbers?
Whenever the derivative equals 0.
Right, set it equal to 0. So we want 0 equals, basically it's the numerator, right? So that obviously occurs at 0. So these are all of our critical numbers right there. Plus and minus 3 and 0. So we'll put them on a number line. Negative 3, 0, and 3. And they're all critical numbers, so I'm going to just put CN on all of them because our domain was all real numbers, right? Okay, test each section into your derivative. Back there, you're going to have to plug it in the top and the bottom. This is the form I'd probably use right there. Okay, so let's see. When you plug it in to the left of negative 3, so like negative 4 or something like that, what do you get?
Negative.
Yeah, you get a negative. What about when you plug in something between, like maybe negative 1? What do you get there? Yeah, because you got a cube root of a negative on the bottom, so you're going to have a negative there and then a negative on the top, so it's positive. Okay, and then if you plug in, say, 1, f prime of 1, what do you get? The top is what? Positive. What's the bottom if I plug a 1 in down here? Negative, yeah, so that's negative again. And then f prime of, say, 4 or anything bigger than 4 like that, obviously you're getting positive again there when you plug that in. Okay, so this one did alternate every other time like that, so we're going to say our increasing, let me write this down here, it's increasing from negative 3 to 0, and we'll do like they said, put the brackets, but like I said, you can put parentheses in there, fine. The only thing that I don't like about putting brackets is then when people get the vertical asymptotes, they put a bracket on where the vertical asymptote is, but where you had domain restrictions, those have to be parentheses. So if you put parentheses on everything, you're a little bit safer.
So wouldn't it be parentheses around the negative 3?
Oh. So this one, does the graph exist at negative 3?
Yes.
Yeah, so if the graph exists, even though it's when the derivative didn't exist, it just meant that there was a sharp point at this on the original graph, but they still include that in. The only time they don't include the end is if it was not in the domain. But that's like what I said. To me, it's like, why even bother with that issue? If they're going to give me points for it, no matter what I put, I'm always going to put parentheses because then I don't have to think about the end. So I always put parentheses. I just think it's safer, but whatever. He says to put brackets, but they aren't going to take off points, so I would just do parentheses. So, and then it also increases from 3 to infinity, and then obviously on all infinities you get parentheses, and then decreases from negative infinity to negative 3, and then again from 0 to 3. Now, did we answer everything? We found the increasing and decreasing intervals, but did we answer what they wanted? What else did it say to find?
The local extreme points.
Yeah, the whole points. So we know that the graph went, so if you kind of visualize what's going on here, I'll just do it with a little highlighter here. The graph is going down, then it changes and goes up, then it changes and goes down, and then it changes and goes up, like that, right? That's kind of the idea of what's going on there. It doesn't look quite like that because it's got sharp points at 3 and -3. But basically, this is what you have here. So where does it have a point of inflection, or not, excuse me, not a point of inflection, a critical number? Okay, I've got to get my vocabulary straight here. Where does it have a local or relative extrema? What x values?
-3, 0, and 3.
Right, all three of them. Which ones are minimums? Right, these are the minimums. See how it's going down and then up, that you went from a negative slope to a positive slope here. So the relative minimums, or the local minimums, whichever you want to call it, are at x equals 3 and -3. But they said, usually we just write at x equals. But they said the points, so we're going to have to give the entire points here. If they don't tell you that, you just say at x equals. And then the relative maximum, obviously, is going to be at 0. So how do I get the whole point here for this? What do I do? How do I get those y values? Yeah, in the original one. Biggest mistake on this is people plug it into the derivative again, because you've been used to plugging things into the derivative to find increasing and decreasing. But it goes back to the original. So go back to your original function up there and plug in. What do you get when you plug in 3 or -3? 0, yeah. So that one's pretty easy. But what do you get when you plug in 0 then? Cube root of 81, yeah. It's -9 to the 2/3 power, which is 81, that's squared, cube root of that. So cube root of 81. And we have all of our answers. So that cube root of 81, you could have just left it as -9 raised to the 2/3 power. This would have been fine too. They don't care if you simplify that. Okay. All right, so let's go on to number 2. I'm going to have to do some erasing here because I don't have any room. All right, so numero 2. Okay, what do we do? What's our first step? The derivative? What do we have to think about even, like, well, what's the other first step? Domain. What's the domain of this? What's the domain of sine? You can just do it individually. What's the domain of x? What's the domain of sine of x? Yeah, it's all real. So think about the sine graph, goes on forever. It's just a little wiggly snake thing. And x is obviously a line. So this is all reals. But look what they gave us. Yeah, they only want us to do this on this section, which is nice because if you think about sine, I mean, how many maxes and mins are you going to have on sine? For infinite, right? So our number line is actually going to only go, I'm going to put parentheses on here because it's going to not even include the ends. So I'll put parentheses on my ends. That's the only part of the number line we're worried about. Okay, all right, so then what do we do? There you go, derivative. So the derivative of x is 1. What's the derivative of sine? Cosine, 2 cosine of x. Okay, it exists everywhere too, right? So there's no place where you have it does not exist. So just set it equal to 0. If we solve this then, we'll move our 1 over and divide by 2, by negative, so -2. Of -1 divided by -2 is a half. Where is cosine of x equal to a half? Just on this interval from 0 to pi. Cosine is your which value, your x or your y on your unit circle? It's the x value. So where do you have an x value of a half? Yeah, pi thirds up here. Because this is 1/2 and then square root of 3 over 2, that little triangle. If you guys want to look at origins of the unit circle, like Google it or something like that, or look at triangles on the unit circle. If you Google that, you can get, I know some of you guys just memorize that unit circle, but it's really not a memorization thing. I mean, it does help to memorize it, but really looking at the origins that it came from, those triangles, I never have to memorize it because I just think of the triangles. Okay, so this is a half, it occurs at, cosine is a half at pi thirds. And then where else?
5 pi thirds.
Yeah, 5 pi thirds goes down here. Okay, those are our two values. Let's put them on there. Pi thirds and 5 pi thirds. Okay. So now we just need to check each interval. Remember, you're doing this in the derivative. So y prime at, I don't know, let's do pi fourths. That's an easy one because pi fourths is below pi thirds, right? Between 0 and pi thirds. So what do you get? Let's see, we get pi fourths for x minus 2. What's the sine of pi fourths? Oops, cosine of pi fourths, sorry. And that's a 1. Okay, what did I do wrong? Where was I plugging it? Yeah, in the original. That's another mistake that people make, is that they plug it back into the original. We're plugging it into this one. I even circled it, but then my eyes glanced up to the other one. So 1 minus 2, what's the cosine of pi fourths? Square root of 2 over 2, or just 1 over square root of 2, whichever you want. But this is kind of nice because it'll cancel. So can you think, just without a calculator, what's the square root of 2 about? Between what numbers? Is it bigger or smaller than 1?
A little bit bigger.
A little bit bigger, yeah. It's like 1.4-ish. So is this going to be positive or negative? Negative. Yeah, there we go. So that section's negative. Then do y prime at, I think 0 would probably be the easiest. Or not 0, sorry, pi. 0 is, I was thinking between the wrong things there. Right in the middle would be pi. That'd be easiest. So you'd have 1 minus 2 cosine of pi. What's cosine of pi? 1? Negative 1. So this is negative 1. So what are you going to have here, positive or negative? 1 minus 2 times negative 1. Positive, yeah, positive. 1 plus 2. So that's positive. And then do 1 on the other end. It's probably going to be negative because this is going to be very symmetrical. Well, not symmetrical, but same type of idea here. So we'll do maybe, let's see, what's on the other side of that? 7 pi fourths. Okay, so you're down here at 7 pi fourths. 1 minus, what's the cosine down there? Square root of 2 over 2, so cosine of pi fourths. That's 1 minus 2 times square root of 2 over 2. Same thing that we got before, so it's again negative. Okay, so we can say it's increasing from pi thirds to 5 pi thirds, and on those, could we put parentheses or brackets? Does it matter? No, doesn't matter. And then decreasing from from 0 to pi thirds. Do these matter if we put parentheses or brackets? One of them does. Which one matters?
0.
The 0, because they said not to include it. So we definitely don't want to include that. The other side could have a parenthesis or a bracket. And then we've got 5 pi thirds and the same thing. The 2 pi has to have a parenthesis on it. Okay, so it could be that, or you could have put brackets here, 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 and here. All right? Okay, so they wanted the points on these. So we're not done here. Where do we have a relative maximum? What x value?
5 pi thirds.
Right, because it's going up and then down right here. So it's up and then down. So you got to have a relative max right there at 5 pi thirds. And where do we have a relative minimum? Pi thirds, yeah. Okay, so go back to your original, plug those in, and get the y values there. I'm going to actually just leave these. I'm going to move this parenthesis over a little bit because I'm just going to leave them in their unsimplified form. So you'd plug in 5 pi thirds up there, and you get 5 pi thirds minus 2 times the sine of 5 pi thirds. What's the sine of 5 pi thirds? Right, this is the point 1/2 and then negative square root of 3 over 2. That's a really bad square root of 3. Let me rewrite it. Still not very good. Well, and that's a 2. Okay, so when we put it in there, a negative is going to change it to positive, and it's square root of 3 over 2, so the 2's are going to cancel here, so I'm going to just write plus square root of 3. You could have left it as 2 times square root of 3 over 2. And then the other one, pi thirds, it's going to be pi thirds minus square root of 3, right? Because it's the same thing except for we're up in the first quadrant now, so it'll be minus 2 times square root of 3 over 2. Okay, so there's our relative max and min. There's our increasing and decreasing intervals. And we've answered everything. We go back. I would suggest that when you're doing questions on an AP exam or in this class or whatever, that you read the question, you start doing your work, and then before you move on to the next question, read the question again and make sure you answered what they were supposed to. All right, let's move on here. Okay, so we're on number 3. So we've got our number line. What's the domain here? Right, x can't equal 0. So put that on your number line and put vertical asymptote on it. Okay, we know it's vertical asymptote because it doesn't cancel with the numerator anywhere. Okay, then what do we have to do? What's our next step? Derivative. Okay, you guys go ahead and do this. I'm going to pause the video here. So at this point, if you're watching this at home, make sure you pause the video and try this problem on your own and then turn it back on. So first I did the derivative there. First the domain is everything except for 0, so we put that on the number line, vertical asymptote. And then we have our critical numbers. We got them at -1 and +1, and that was from doing the domain, doing the derivative here and then simplifying it to get this. And then we set that equal to 0, which is the numerator equal to 0. We end up getting our critical numbers. And we put those on the number line, and then we plug in values within each section on the number line. And that tells us our increasing and decreasing sections then. Labeled those on my number line. And then the relative max and min, then you've got at -1 for the relative max and at 1 for the relative min, and then get the y coordinates, plugging them back into the y. That's right where you should be. Okay, so here's another one. What's the domain? Is there any place where you have a fraction with the denominator that you can't do, or is there any place where you have a square root of a negative? What do you think?
No.
Be really careful.
Yeah, because the exponent's negative.
Right, the exponent's negative. That's tricky because this is really negative x over e to the positive 2x squared. So, but why did you say no, though?
That can't equal 0.
Exactly. E to anything, e to the 2x squared can never equal 0, right? The graph of e to the x, yeah, you take any positive number and you raise it to any power, even the 0 power, and you don't get a negative number. So it's still all real. So I'm glad you thought of that. It's always really good to go through all these kind of things, but the domain here does end up being all real numbers. Very good. Okay, and then go ahead and do your derivative. What rule are we using? Product rule, yeah. First times the derivative of the second. Be careful, you got to use the chain rule on that second one. Now you could have rewritten it like this and used the quotient rule if you wanted to. Either way is fine. Okay, so I simplified a little bit there. I've got to set it equal to 0 now. Again, this one is gonna be domain of all reals on here, right? Because even if we move those e to the 2x squared down in the denominator, we're still gonna have all reals. How do I solve this?
Factor out e to the negative 2x.
Very good. Factor out e to the negative 2x squared, and we end up with 4x squared plus 1. Is that right? I think I have a minus there somewhere. I need, oh, this is a negative 1, so I should have had a minus right here. I was going to say that would be no answers. There we go. That's a little better. So we said each one of these equal to 0, but we already said, does this ever equal 0, e to the negative 2x? E to anything, is it ever going to be 0? Yeah, that's never 0, so that doesn't give us any critical numbers. But set the other part equal to 0. Yeah, 1/2 and what else? Negative 1/2, yeah. If you're going to solve this by moving the 1 over and dividing by 4, don't forget when you put the square root on that you have to do plus or minus on that. So this is plus or minus 1/2. If you factor it, you can see there's two things here. Okay, so we'll draw our number line, put our negative 1/2 on, our positive 1/2. Test them. What do we end up with here? What do you think? What's the first one on the left? What do you get? Remember, you're plugging back into the derivative there. What do you get? Do you get negative? Like f prime of, say, negative 1. So you'd get a 4 times something positive. I'm not even going to worry, but actually, let's just stick it into this section right here because I know that's always positive, right? So all I have to do is stick it into this part. So if we plug in a negative 1, we're going to get a positive value, right? And if we plug in, say, a 0, we get a negative value. If we plug in a positive 1, we get a positive value. So it's plus minus plus. So go ahead and write out your increasing and decreasing intervals. Kind of out of room there. I'm going to write it over here. Increasing. Again, you can put that bracket or parenthesis, whichever you want, on the 1/2. And the negative 1/2, either one. And then don't forget to say your relative max and min points. Remember, you're plugging back into the original function to get these y coordinates here. Okay, double check my work, make sure I did that right. Make sure you get the same thing I did. Okay, our last one here. Were my answers correct over here? Did you guys get the same thing I did? Okay, great. All right, our last one, number 5. So this one's a little bit faster. Obviously, it's a polynomial, so its domain is all reals, right? What do you think it's going to look like? It's an x cubed, a positive x cubed. What's it going to look like? Okay, it could look like this kind of a thing. Does it have to have that wiggle in it? No, it could look like that kind of thing. Who knows? We got it. Usually, if there's things behind it, it does have a wiggle, but not always. Okay, so let's do it. F prime of x. Okay, we set it equal to 0 there. It exists everywhere, right? Factor a 3 out, make it a lot easier. And then factor that guy. What's it factor to?
X minus 1 squared.
Right, x minus 1 times x minus 1. So setting that equal to 0, we divide by 3 and it's gone. So basically it's just this x minus 1 squared equals 0, which is the same thing as just x minus 1 equals 0, right? So we just get x equals 1. We only have one critical number. Let's put it on our number line. Okay, go ahead and plug them in, each side of that. Should be a big clue to you. If you only have one critical number, is this going to have that big wiggle in it? No, because if you had, you'd have to have two critical numbers if it was going to wiggle like that. You'd have a max and a min like that. So this one's going to be the one that doesn't have a wiggle. No wiggling. So you plug in something to the left of 1 into our derivative here in any form, whichever one you want there. And we get a positive. What do you get when you plug it into the right? Also a positive, which makes sense because if it's not going to wiggle, it's going to go like that. Now the derivative at 1 was 0. So this is one of those cases where you had a critical number that you didn't have a max or a min in. So this one is increasing on the entire thing, never decreasing, nowhere, and no extrema. Okay, because in order to be a relative max or a relative min, it has to change from positive to negative or negative to positive. Okay, so that one's a little quicker to do. Polynomials are always awesome. Forget those. They're so much faster than the other ones, usually, as long as they don't get too crazy. Okay, and the last little thing on here is just the note about that. It says, in that last example, we call that strictly monotonic. So mono means one, and so this is one direction. Another name for monotonic, they could have called it one direction. Isn't there a band called that? I think, yeah, there is. There's One Direction. My son listens to it. Strictly, so that means it's always increasing or always decreasing, all right? So 2 important points. Not every critical number produces a maximum or minimum. Even though the slope at x equals 1 was 0, the function is always increasing on that one. Okay, I believe that's it for this lesson.